This is the Large Hadron Collider. It's 27 kilometers in circumference. It's the biggest scientific experiment ever.
Over at the Large Hadron Collider, protons simultaneously circle clockwise and counterclockwise, smashing into one another while moving at 99.999991% the speed of light apiece.
And it accelerates protons around in a circle, both ways. One beam goes one way, one goes the other way, and they go around 11,000 times a second. So that's very close to the speed of light, 99.999999% the speed of light. And then we cross the beams and collide the particles. And in those collisions, you're recreating the conditions that were present less than a billionth of a second after the Big Bang.
After billions upon billions of collisions at these enormous energies, the LHC has brought us further in our hunt for the fundamental nature of the universe and our understanding of the elementary building blocks of matter. However, despite these successes in a recent shocking revelation, world-renowned physicist Brian Cox has exposed that during a test with unprecedented energy levels, something terrible happened at CERN, and no one can explain.
There are many other things. You've heard many of the big problems picture. One of the wonderful things, actually, I find, is that we've discovered any of them when you realize how tiny they are.
Could this unexpected discovery unlock more secrets of our vast universe? Or will it provide a brand new doomsday scenario? Join us as we dig deep into the new findings that baffle even the most seasoned researchers. CERN's Large Hadron Collider, as you know, is the most powerful particle accelerator in Earth's history, capable of reaching energies of approximately 7 tetraelectrovolts per particle. That equates to accelerating protons to 299,792,455 meters per second apiece, just 3 meters per second shy of the maximum achievable speed in the universe, the speed of light. For years, since it first turned on in 2008, the LHC has been colliding as many protons with other protons by bunching them together, circulating them in both the clockwise and counterclockwise directions in its large ring, timing their motions so that the bunches intersect at particular collision points, where large detectors are awaiting those collisions, and they measure at a series of distances the energy, momentum, charge, spin, and other properties of the particles that arise in the aftermath of that collision. By measuring what comes out of those collisions and comparing those experimental results with the theoretical predictions that arise from both standard model-only scenarios as well as beyond the standard model scenarios, you can determine how well the standard model by itself fits what you've observed.
But it's a tremendously successful thing now, and it's operating beyond its design capabilities. It's quite incredible.
Any departures from it, so long as they're robust enough, are something that will make the entire community sit up and take notice. Prior to the LHC, we had discovered some remarkable cracks in the facade of the standard model, things that came as surprises to us. We discovered that neutrinos and antineutrinos weren't massless and didn't remain the same species of particle, but rather had a non-zero rest mass and would oscillate from one flavor to the others, particularly when they interacted with matter. We discovered that dark matter exists, and were able to rule out all of the standard model particles as viable candidates for it. We discovered the accelerated expansion of the universe, which we attribute to a new form of energy, which again cannot be explained by anything within the standard model. We knew that there was no CP violation in the strong interactions, only in the weak interactions, despite the fact that the standard model allows for both. If a spinning particle decays, the antiparticle counterpart that spins in the opposite direction is observed to behave differently under the weak interactions, but not the strong interactions, and nobody knows why. And finally, we live in a universe made predominantly of matter and not antimatter. But the laws of physics do not have enough of an asymmetry between them to create the matter-rich universe we inhabit today. In many ways, even before the Large Hadron Collider turned on for the first time, we knew that there must be more to the universe than the standard model gives us. But at particle colliders, where we take matter, and sometimes antimatter, smash it together at high energies, and observe the particle debris that comes out, there have been no observations or measurements that have stood the test of time that run counter to the Standard Model's predictions. When the LHC began colliding particles, it was the last good hope for many theoretical ideas that had been bandied about as plausible explanations for what could be out there beyond the Standard Model for many decades. In 2012, the Large Hadron Collider achieved a truly monumental feat. This underground particle accelerator along the French-Swiss border detected for the first time the Higgs boson, a particle that had eluded physicists for decades. The Higgs boson, sometimes referred to as the God particle, is a cornerstone of the Standard Model. This particle gives other particles their mass and creates the distinction between the weak nuclear force and the electromagnetic force. But as Brian Cox said, with the good news came some bad.
These are big mysteries that there's something really profound we don't understand about the way that stuff, in particular the Higgs, actually interacts with space and time. So very naively, the Higgs should blow the universe apart.
The Higgs had a mass of 125 giga-electron volts, which was orders of magnitude smaller than what physicists had thought it should be. To be perfectly clear, the framework physicists use to describe the zoo of subatomic particles, known as the Standard Model, doesn't actually predict the value of the Higgs mass. For that theory to work, the number has to be derived experimentally. But back-of-the-envelope calculations made physicists guess that the Higgs would have an incredibly large mass. So once the champagne was opened and the Nobel Prizes were handed out, the question loomed. Why does the Higgs have such a low mass? In another, and initially unrelated problem, the strong force isn't exactly behaving as the Standard Model predicts it should. In the mathematics that physicists use to describe high-energy interactions, there are certain symmetries. For example, there is the symmetry of charge, change all the electric charges in an interaction and everything operates the same. The symmetry of time, run a reaction backward and it's the same. And the symmetry of parity, flip an interaction around to its mirror image and it's the same. In all experiments performed to date, the strong force appears to obey the combined symmetry of both charge reversal and parity reversal. But the mathematics of the strong force do not show that same symmetry. No known natural phenomena should enforce that symmetry, and yet nature seems to be obeying it. What gives? A pair of theorists, Raffaele Tito D'Agnolo of the French Alternative Energies and Atomic Energy Commission, and Daniele Teresi of CERN, thought that these two problems might be related. In a paper published in January to the journal Physical Review Letters, they outlined their solution to the twin conundrums. Their solution: the universe was just born that way. They invoked an idea called the multiverse, which is born out of a theory called inflation. Inflation is the idea that in the earliest days of the Big Bang, our cosmos underwent a period of extremely enhanced expansion, doubling in size every billionth of a second. Physicists aren't exactly sure what powered inflation or how it worked, but one outgrowth of the basic idea is that our universe has never stopped inflating. Instead, what we call our universe is just one tiny patch of a much larger cosmos that is constantly and rapidly inflating and constantly popping off new universes, like foamy suds in your bathtub. Different regions of this multiverse will have different values of the Higgs mass. The researchers found that universes with a large Higgs mass find themselves catastrophically collapsing before they get a chance to grow. Only the regions of the multiverse that have low Higgs masses survive and have stable expansion rates, leading to the development of galaxies, stars, planets, and eventually high-energy particle colliders. To make a multiverse with varying Higgs masses, the team had to introduce two more particles into the mix. These particles would be new additions to the Standard Model. The interactions of these two new particles set the mass of the Higgs in different regions of the multiverse. And those two new particles are also capable of doing other things. The newly proposed particles modify the strong force. leading to the charge parity symmetry that exists in nature. They would act a lot like an axion, another hypothetical particle that has been introduced in an attempt to explain the nature of the strong force. The new particles don't have a role limited to the early universe either. They might still be inhabiting the present-day cosmos. If one of their masses is small enough, it could have evaded detection in our accelerator experiments, but would still be floating around in space. In other words, one of these new particles could be responsible for the dark matter, the invisible stuff that makes up over 85% of all the matter in the universe. It's a bold suggestion, solving two of the greatest challenges to particle physics and also explaining the nature of dark matter. However, it's worth noting that while the Higgs boson is great at providing new insights, it does have the potential to create something hazardous. The fact it is the foundation of mass for all existing matter means it also has the potential to wipe out the universe. Stephen Hawking once warned us that humans might accidentally disturb the Higgs field as technology advances, causing everything to disappear instantly. The Higgs potential has the worrisome feature that it might become metastable at energies above 100 billion giga-electron volts. This could mean that the universe could undergo catastrophic vacuum decay, with a bubble of the true vacuum expanding at the speed of light. This could happen at any time and we wouldn't see it coming. Put simply, the God particle could create a new way the world ends, not with a bang, but with a quantum vacuum decay of the ground state of the universe to its true minimum. What's notable, this Higgs doomsday scenario is not unfounded. The universe underwent radical phase transitions in the past. For those who don't know, phase transitions are when a substance undergoes a rapid radical transformation. They happen all the time. For instance, you boil water, and it transforms from a liquid into a gas. You cool that same water, and it turns into a block of ice. Perhaps the most exotic phase transitions are those that happen to quantum fields. Quantum fields are the fundamental building blocks of the universe. Every kind of particle, say a photon or an electron, is really just a local manifestation of an underlying field. That field soaks all of space and time like bread dipped in olive oil. The way those fields interact and communicate with each other makes up the forces and physics of our existence. That existence is based on four fundamental forces: gravity, the weak force, electromagnetism, and the strong force. But it hasn't always been this way. In the earliest moments of the cosmos, those forces were united. As the universe expanded and cooled, the quantum fields underwent phase transitions, splitting apart one by one. The last phase transition occurred when the electromagnetic force split from the weak force. That splitting gave rise to the photon and the W and Z bosons, the carriers of those two forces. Since that event, which happened when the universe wasn't even a second old, everything's been stable. No more splitting. No more phase transitions. The four forces of nature went on to shape and sculpt the evolution of the cosmos for billions of years. As far as everything looks, it's all stable, but it might not last forever. Our best bet at probing the stability of the universe is through the mass of the Higgs boson. The Higgs is a very interesting field. Its presence in the universe is what separated the electromagnetic force from the weak force, and what maintains that split today. Without the Higgs boson, those forces would merge right back together. In quantum physics, the more massive an entity is, the more unstable it is. Massive particles quickly decay into lighter ones, for example. So if the Higgs is very massive, it might not be as stable as it seems, and it might decay into something else someday. But if the Higgs is light enough, it's likely to hang out forever, and there's nothing more to say about the future of the quantum fields of the universe. Measurements of the Higgs have found that its mass puts the universe smack in between the really honestly stable and, oh no, it looks a little unstable regimes. Physicists call this state metastable, a situation that is stable for now, but could quickly deteriorate if something were to go wrong. The apparent metastability of the quantum fields of the universe is a little unsettling. Although it could mean that the universe could persist for billions, even trillions of years without anything going wrong at all, it could also mean that the universe is already beginning to transform. All it would take is one little shake in the wrong direction, in some random patch of the universe where the Higgs falls apart and the underlying quantum fields find a new, more stable configuration. That region of new universe would then propagate outward at nearly the speed of light through the old universe. This kind of phase transition is called a false vacuum decay. It references the idea that the vacuum of our universe is a false one. It's not as stable as it might appear, and it will someday decay into something new. By the time we received any information that the phase transition was upon us, it would already be happening. What would be on the other side of that new universe? It's impossible to say. It might be totally mundane, with the new quantum fields looking exactly like the old quantum fields, and nothing amiss. It could be just a slight adjustment, like a little tuning to the nature of dark energy, or a slight adjustment to the masses of neutrinos. Or it could be radically different, with a universe filled with brand new forces, fields, and particles, which would make life as we know it impossible. Of course, we're not even 100% sure about the metastability criterion. We know that the standard model of particle physics is incomplete. A complete version could rewrite our understanding of quantum fields and where the stable-unstable line is drawn. Nevertheless, it is more essential to test the ability of the LHC and prevent this from happening if it were to be true. In what ways can humans disturb the field? How can CERN scientists test out vacuum decay in the LHC with the Higgs boson? Well, there must be some burning questions that the CERN should be concerned about. Ultimately, it is up to scientists to utilize the largest machine in the world and uncover more secrets of the universe. The capability of the collider is not a big problem for doing certain tasks, but the key is to come up with theories and ideas that can be investigated and proven. The LHC is only a machine that transforms our ideas into reality, so we must be actively thinking and questioning ourselves how we can challenge the machine by implementing new concepts. So far, the discovery of the Higgs boson has contributed to explaining why most things have mass and why they exist in the universe like each of us does. And recently, it discovered more new fundamental particles. The LHC is the powerhouse of colliding high-energy particles. It is also the heart of proving our existence. Perhaps one day, each of us can somehow create our own personalized universe. Regardless, CERN's colliders have tapped not only the wonders of the universe, but also the fears of our age. What would happen if you stuck your body inside a particle accelerator? The scenario seems like the start of a bad Marvel comic, but it actually happened in an awful accident in 1978. And on July 13, 1978, a Soviet scientist named Anatoly Bugorsky stuck his head in a particle accelerator. On that fateful day, Bugorsky was checking malfunctioning equipment on the U-70 synchrotron, the largest particle accelerator in the Soviet Union, when a safety mechanism failed and a beam of protons traveling at nearly the speed of light passed straight through his head, Phineas Gage style. It's possible that, at that point in history, no other human being had ever experienced a focused beam of radiation at such high energy. Although proton therapy, a cancer treatment that uses proton beams to destroy tumors, was pioneered before Bugorsky's accident, the energy of these beams is generally not above 250 million electron volts, a unit of energy used for small particles. Bugorsky might have experienced the full wrath of a beam with more than 300 times this much energy, 76 billion electron volts. Proton radiation is a rare beast indeed. Protons from the solar wind and cosmic rays are stopped by Earth's atmosphere, and proton radiation is so rare in radioactive decay that it was not observed until 1970. More familiar threats, such as ultraviolet photons and alpha particles, do not penetrate the body past skin unless a radioactive source is ingested. Russian dissident Alexander Litvinenko, for instance, was killed by alpha particles that do not so much as penetrate paper when he unknowingly ingested radioactive polonium-210 delivered by an assassin. But when Apollo astronauts protected by spacesuits were exposed to cosmic rays containing protons and even more exotic forms of radiation, they reported flashes of visual light, a harbinger of what would welcome Bugorsky on the fateful day of his accident. According to an interview in Wired magazine in 1997, Bugorsky immediately saw an intense flash of light but felt no pain. The young scientist was taken to a clinic in Moscow with half his face swollen, and doctors expected the worst. Ionizing radiation particles such as protons wreak havoc on the body by breaking chemical bonds in DNA. This assault on a cell's genetic programming can kill the cell, stop it from dividing, or induce a cancerous mutation. Cells that divide quickly, such as stem cells in bone marrow, suffer the most. Because blood cells are produced in bone marrow, for instance, many cases of radiation poisoning result in infection and anemia from losses of white blood cells and red blood cells, respectively. But unique to Bugorsky's case, radiation was concentrated along a narrow beam through the head, rather than being broadly distributed from nuclear fallout, as was the case for many victims of the Chernobyl disaster or the bombing of Hiroshima. For Bugorsky, particularly vulnerable tissues, such as bone marrow and the gastrointestinal tract, might have been largely spared. But where the beam shot through Bugorsky's head, it deposited an obscene amount of radiation energy, hundreds of times greater than a lethal dose by some estimates. And yet, Bugorsky is still alive today. Half his face is paralyzed, giving one hemisphere of his head a strangely young appearance. He is reported to be deaf in one ear. He suffered at least 6 generalized tonic-clonic seizures. Commonly known as grand mal seizures, these are the seizures most frequently depicted in film and television, involving convulsions and loss of consciousness. Bugorsky's epilepsy is likely a result of brain tissue scarring left by the proton beam. It has also left him with petit mal or absent seizures, far less dramatic staring spells, during which consciousness is briefly interrupted. There are no reports that Bugorsky has ever been diagnosed with cancer, though that is often a long-term consequence of radiation exposure. Despite having nothing less than a particle accelerator beam pass through his brain, Bugorsky's intellect remained intact, and he successfully completed his doctorate after the accident. Bugorsky survived his accident, and as frightening and awesome as the inside of a particle accelerator might be, humanity has thus far survived the nuclear age. A significant note, although the LHC has brought us further in our hunt for the fundamental nature of the universe and our understanding of the elementary building blocks of matter after billions upon billions of collisions at these enormous energies, no new particles, interactions, decays, or fundamental physics has been found. Worst of all is this. Most of CERN's data from the LHC has been discarded forever. This is one of the least well-understood pieces of the high-energy physics puzzle, at least among the general public. The LHC hasn't just lost most of its data. It's lost a whopping 999.997% of it. That's right. Out of every 1 million collisions that occurs at the LHC, only about 30 of them have all of their data written down and recorded. It's something that happened out of necessity due to the limitations imposed by the laws of nature themselves, as well as what technology can presently do. But in making that decision, there's a tremendous fear made all the more palpable by the fact that, other than the much-anticipated Higgs, nothing new has been discovered. The fear is this, that there is new physics waiting to be discovered, but we've missed it by throwing this data away. We didn't have a choice in the matter, really. Something had to be thrown away. The way the LHC works is by accelerating protons as close to the speed of light as possible in opposite directions and smashing them together. This is how particle accelerators have worked best for generations. According to Einstein, a particle's energy is a combination of its rest mass, which you may recognize as E equals mc squared, and the energy of its motion, also known as its kinetic energy. The faster you go, or more accurately, the closer you get to the speed of light, the higher energy per particle you can achieve. As told, at the LHC, we collide protons together at 99.999991% the speed of light apiece. By smashing them together at such high speeds, moving in opposite directions, we make it possible for otherwise impossible particles to exist. The reason is this: all particles that we can create have a certain amount of energy inherent to them, in the form of their mass at rest. When you smash two particles together, some of that energy has to go into the individual components of those particles, both their rest energy and their kinetic energy. But if you have enough energy, some of that energy can also go into the production of new particles. This is where E equals mc squared gets really interesting. Not only do all particles with a mass have an energy inherent to their existence, but if you have enough available energy, you can create new particles. At the LHC, humanity has achieved collisions with more available energy for the creation of new particles than in any other laboratory in history. The energy per particle is around 7 TeV, meaning each proton achieves approximately 7,000 times its rest mass energy in the form of kinetic energy. But collisions are rare, and protons aren't just tiny, they're mostly empty space. In order to get a large probability of a collision, you need to put more than one proton in at a time. You inject your protons in bunches instead. At full intensity, this means that there are many tiny bunches of protons going clockwise and counterclockwise inside the LHC whenever it's running. The LHC tunnels are approximately 26 kilometers long, with only 7.5 meters separating each bunch. As these bunches of beams go around, they get squeezed as they interact at the midpoint of each detector. Every 25 nanoseconds, there's a chance of a collision. So what do? Do you have a small number of collisions and record every one? That's a waste of energy and potential data. Instead, you pump in enough protons in each bunch to ensure you have a good collision every time two bunches pass through. And every time you have a collision, particles rip through the detector in all directions, triggering the complex electronics and circuitry that allow us to reconstruct what was created when and where in the detector. It's like a giant explosion, and only by measuring all the pieces of shrapnel that come out can we reconstruct what happened at the point of ignition. The problem that then arises, however, is in taking all of that data and recording it. The detectors themselves are big, 22 meters for CMS and 46 meters long for Atlas. At any given time, there are particles arising from 3 different collisions in CMS and 6 separate collisions in Atlas. In order to record data, there are 2 steps that must occur. First off, the data has to be moved into the detector's memory, which is limited by the speed of your electronics. Even though the electrical signals travel at nearly the speed of light, we can only remember about 1 in 500 collisions. Then, the data in memory has to be written to disk or some other permanent device, and that's a much slower process than storing data in memory. Decisions need to be made as to what's kept and what's discarded. Now, there are some tricks we use to ensure that we choose our events wisely. We look at a variety of factors about the collision immediately to determine if it's worth a closer look or not, what we call a trigger. If you pass the trigger, you make it to the next level. Then a second layer of filters and triggers is applied. If an event is interesting enough to get saved, it goes into a buffer to ensure it gets written to storage. We can make sure that every event that gets flagged as interesting is saved, along with a small fraction of uninteresting events as well. That's why, with the necessity of taking both of these steps, only 0.003% of the total data can be saved for analysis. How do we know we're saving the right pieces of data? the ones where it's most likely we're creating new particles, seeing the importance of new interactions, or observing new physics. When you have proton-proton collisions, most of what comes out are normal particles, in the sense that they're made up almost exclusively of up and down quarks. This means particles like protons, neutrons, and pions. And most collisions are glancing collisions, meaning that most of the particles wind up hitting the detector in the forwards or backwards direction. So, to take that first step, we try and look for particle tracks of relatively high energies that go in the transverse direction, rather than forwards or backwards. We try and put into the detector's memory the events that we think had the most available energy for creating new particles of the highest mass possible. Then, we quickly perform a computational scan of what's in the detector's memory to see if it's worth writing to disk or not. If we choose to do so, it can be queued to go into permanent storage. The overall result is that about 1,000 events every second can be saved. That might seem like a lot, but remember, approximately 40,000 bunches collide every second. We think we're doing the smart thing by choosing to save what we're saving, but we can't be sure. In 2010, the CERN data center passed an enormous data milestone, 10 petabytes of data. By the end of 2013, they had passed 100 petabytes of data. In 2017, they passed the 200 petabyte milestone. But for all of it, we know that we've thrown away, or failed to record, about $30,000 times that amount. We may have collected hundreds of petabytes, but we've discarded and lost forever many zettabytes of data, more than the total amount of internet data created in a year. It's eminently possible that the LHC created new particles, saw evidence of new interactions, and observed and recorded all the signs of new physics. And it's also possible, due to our ignorance of what we were looking for, we've thrown it all away and will continue to do so. The nightmare scenario of no new physics beyond the standard model appears to be coming true. But the real nightmare is the very real possibility that the new physics is there. We've built the perfect machine to find it, we've found it, and we'll never realize it because of the decisions and assumptions we've made. The real nightmare is that we've fooled ourselves into believing the standard model is right, because we only looked at 0.003% of the data that's out there. We think we've made the smart decision in keeping what we've kept, but we can't be sure. It's possible that the nightmare is one we've unknowingly brought upon ourselves. The real nightmare is the very real possibility that the new physics is there. We've built the perfect machine to find it, we've found it, and we'll never realize it because of the decisions and assumptions we've made. The real nightmare is that we fooled ourselves into believing the standard model is right, because we only looked at 0.003% of the data that's out there. We think we've made the smart decision in keeping what we've kept, but we can't be sure. It's possible that the nightmare is one we've unknowingly brought upon ourselves. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.